One type of function is a polynomial. We have already seen two examples of polynomials: a linear function and a quadratic function. We can also have a constant function equal to 1 and the same number for all values of x. These are examples of polynomials. More in general is if you have powers of x, for example x to the nth power, and then we have some coefficient, that is some constant before that, multiplied here. Let's call the constant an, and an minus 1, xn minus 1. So if you have a function of this form, then it's called a polynomial. So this is a polynomial function. For example, 6x5 minus 3x4 plus x2 minus square root of 2. This is a polynomial. So we have here constants, and then we have powers of x. So we could have many different types of polynomials. Having defined a polynomial, we can now define a rational function. So if we have two polynomials, let's call them px and qx. If we make the quotient between these two, then this is an example of a rational function. So for example, if we have a polynomial in the numerator, 2x3 minus 7x, and then in the denominator we have another polynomial, x squared plus 3. This is a rational function. So we have a division of two functions, polynomials. A simple example is, for example, 1 over x. Since 1 is a polynomial and x is a polynomial, so this is a simple example of a polynomial. Or for example, 1 over x squared. We can also have minus in front here, since we could have put the minus up here. So these are examples of rational functions. We have talked about two variables being proportional. That means they are related like this, where k is some constant. If we instead have that y and x are related in this way, then we call its inverse proportional to each other. And this is an example of a rational function, because we can write it as k over x. So inverse proportionality is example of a rational function. For example, if you drive a distance, if you want to drive some distance s, and you drive with some speed v and time t. Let's say that you travel a certain distance of 10 kilometers, and you travel with some speed here, v. Then the time for this distance is t. Let's say that we now want to find out how long time does it take, depending on the speed. Then we can divide v on both sides, then we get like this. And this we can write as 10 times 1 over v. So we see that the time it takes to travel 10 kilometers is inversely proportional to the speed. So if we double the speed, then we half the time. And if we half the speed, we double the time. So they're inversely proportional. How does an inverse proportional function look like? For example, if we take 1 over x, then we see it looks like this, where we have a function like this inverse proportional. And of course, if we take instead 5 over x, the curve is a little bit higher up. And we also have for the negative part, you see it's below the x-axis. And if we have some rational function, for example, first of all, we can take x squared, 1 over x squared. Then it looks like this. Then you see it's symmetrical on the left or right of the y-axis, since if we square it, the negative numbers disappear, or the negative sign disappears. And let's say we take, for example, this function, x plus 1 divided by x minus 1. And it looks like this. Okay, it looks similar to what we had for 1 over x, but it's not exactly the same. The reason is that this is close to that, but it's transformed a little bit to the right. So we see that when x is 1, here in the denominator, when x is 1, this becomes 0. So this blows up, it goes to infinity and negative infinity. So let us zoom out. So if we zoom out, we see that the function goes down here, it approaches some horizontal line. And actually it approaches the horizontal line y equal to 1. So we see that it approaches this line, horizontal line. So one say that this line here, this black line, that's called a horizontal asymptote. A horizontal asymptote for this function, because the function approaches this when x goes to infinity. And it also approaches the function when here it goes to negative infinity. So this is an asymptote when x goes to plus or minus infinity. Then we also have vertical asymptotes. In this case, we have a vertical asymptote when x equals 1. So for this line here, so if you change the color for that to red, we see that our function approaches this line when x comes closer to 1. So when we come close to 1, this function approaches this vertical straight line, and the same on the other side as it approaches to the negative. So you say that this red line here is a vertical asymptote for the curve. And then we can also have cases of oblique asymptotes. So straight lines that are neither horizontal or vertical. So for example, if we take away these and instead draw the following function, x squared plus 1 divided by x minus 1. Then we have this function. And then one sees that one has an asymptote that is x plus 1. The straight line x plus 1, this. So if you change the color for that to green, we see that our function approaches this line, this green line, when x goes to infinity and x goes to minus infinity. So that is called an oblique asymptote. So an asymptote is a straight line that the function approaches either when x goes to infinity, x goes to minus infinity, or some in-between value as we had for this function here. Then we have the vertical asymptote. So here we have oblique asymptotes. But we will talk about limits of things as x goes to infinity and things like that. We will talk more about later. But it's good to already now have seen something about asymptotes. So asymptotes are straight lines that the functions approaches in limiting cases. For example, when x goes to infinity or minus infinity, or some value in between, as we had for this one. Then we had the vertical asymptote here when x goes to 1.